Hey James,
Hey, Pedro. How are you?
I'm fine. How are you?
Well, I'm going out of town tomorrow and figures I had a tooth problem today, so I spent 3 hours at the dentist today. They were
3
nice.
hours.
Well, maybe not, but I had to go and they were very nice. They squeezed me in, on an emergency
Mm-hmm.
basis. So I called them at 8 in the morning. They said, "Can you come in immediately?"
Mm-hmm.
Drove over there immediately. And then they said, but then they only had a short block of time. So I had to go back in the afternoon. And
Mm-hmm.
the actual work wasn't that long, but I had to wait because of course
Oh,
they had to squeeze me. I mean, I'm
yeah.
not complaining about it. I mean, it was very nice of them to be willing to put me, to put me in when I wasn't on the schedule. So I don't mean
Yeah, that's impressive.
uh,
Coming from the regular United States healthcare, I think
no.
that's it's more than what I would expect.
Well, dentists, you usually, I mean, there's some dental insurance, but mainly you pay out of pocket.
Mm-hmm.
So I think because you pay for it, it it's a little bit less. They're a little bit more flexible. Now, getting a tooth cleaning, regular tooth cleaning, is very hard because there's a shortage of hygienists to clean your teeth.
Mm-hmm.
And so, if I have to reschedule an appointment to have my teeth cleaned, I'll wait 6 months.
Mm-hmm.
But for emergencies, they're pretty good. And it wasn't a
Uh,
huge emergency, but it was something I needed to fix.
yeah. Both my parents are dentists, right?
Ah,
And then my father once told me that the procedures would cost between 10 and $50
um,
in Brazil. And I mean, if you convert that to dollars, it's like $2 to $10 the procedure. And the way they made money is by first the people would uh it's an insurance, so people pay monthly, and then they have to focus on prophylaxis because then people get less procedures.
right.
So they would focus on like teaching people to brush the teeth, take care of it, so on
Uh,
and so forth.
okay, that sounds reasonable.
Yeah. And then, but it's so cheap. I mean, you could get like a canal treatment or something like that for like $50.
Well, I mean, people will fly from the US to Thailand or Mexico or India for surgery
Hmm.
because it's so much less expensive.
Yeah.
And the best hospitals, I'm sure, in Brazil are as good as in the US, or so. But the problem is if it's in a different language and you don't know the system, or there's a problem or you have to go multiple times, then it's not so easy.
Yes. Yeah, exactly. And especially small problems,
No.
small and frequent ones.
Hello. So so you said you had never Jen, Chow, you said you hadn't had dynamical systems, so I'm going to do a little dynamical systems today. I hope that'll be interesting for you.
Okay.
Is that all right? I mean, I could do something else, but since you said you hadn't had a course in dynamical systems, I thought we should do the basic mathematics.
Yeah, I think I can follow.
I'm sure you can follow it. I'm worried it'll be I don't want it to be boring for you.
Oh, it's I believe it would be interesting.
Okay, great. Uh, let's see, give people a minute. I don't I'm sorry for I don't know what happened to our Indian auditor. I know last week there was a problem with the Zoom link, so now let me check to make sure nobody's locked out of the Zoom. I don't know if Rita was going to join us today. Okay. So wait another minute or two. And I mean, if we're going to work on this frequency locking example from Moens Janssen, then the basics of stability theory are going to be important. So it's good to cover. We should cover those. And I apologize if the it looks like it's clearing up. Occasionally, the power will fail in my house when there's a storm. I'm not sure why, but in general, I like my setup here, but if the electricity goes out, I lose my internet connection. And it's raining. I don't know where. Well, you say you're up at Mesh, so actually Mesh is quite close to my house. I live on the basically less than a mile from Mesh, north. So I'll give another minute. Did you have any questions anything you wanted to go over before we start?
No questions. No.
I'll try to get another. I mean, the main thing to do would be to read the papers of the paper of Moens and see if we can begin to understand the frequency locking behavior of that system. And I don't know exactly how far we'll get today with this lecture, but and I don't. You feel free to tell me if I'm going too slowly or too fast. Okay.
Yeah, sure.
This is actually material that I really like to teach. But I often don't, depending on the semester, I don't always get to it. And Rita, you may get on the hook for teaching next week. So
Okay.
this will be material that's very familiar to you. So
Okay, good.
and I have the slide decks ready. So
Okay, it is good, but I'd like to have them beforehand, right? I'll have them.
I'll share all this material with you.
Okay. Okay. So, and it's
We have a total of one student here, so it's a special kind of class.
only one student.
Yeah. Hello.
Hello, Jason. How do we call you? Fu?
Oh, just call me Jen.
Jen.
Yeah,
Okay.
Jen. That's okay.
Okay. Okay. Thank you.
And you have a physics background, right? You said you had.
Yeah, bachelor degree. Yeah.
Oh, good.
So Rita was the chair of. Are you still chair of your department, or not
And
anymore?
I was chair of the postgrad course. No, I'm not. Thank God, I'm not anymore. Yeah, that was. I served for 2 years, and this is the least thing I could do. That's enough.
So Rita is a very distinguished statistical physicist.
Oh,
Who's visiting IU for a year.
nice to meet you.
Okay.
Okay.
It's,
Well,
it's
I
very
guess
generous.
I guess I'll get started here. Welcome back. This is, I think, lecture 7. since we missed a week, of Introduction to Dynamics on Networks. And today I'm going to be talking about the basics of linear stability theory and bifurcation. So this is going to be more mathematical, although we'll tie back the material to the examples that we're going to be doing biologically in class. As always, I need to remind people that this class is live streamed and recorded on YouTube. So if you want to refer to the lectures afterwards, you have those available. And actually, we already last week, by the back door, started doing bifurcation analysis and stability theory, but without explaining the mathematics. And so now I want to come back and talk a little bit about that. So we're going to start out by explaining the concept of stability. We'll do the basic mathematics of one-dimensional stability, which is simple and the easiest thing to do. Well, then there's a beautiful theorem which I'll show you about stability. And then we will do one or two simple exercises just to check our understanding 1D stability. Then I will go on and we'll start talking about higher dimensional dynamics, introduce you to the concept of null lines, which are primarily useful for doing sketches. If you're going to do a stability analysis in 2 dimensions and you don't want to do a lot of computing, the null lines are very useful in helping you understand things without having to do any math. But they're not that intuitive until you practice them. And then, depending on how much time we have, we'll do exercises. The ones we don't get to, we'll do as homework. And then probably this will wind up being next week's lectures. That will talk about the stability theory in arbitrary dimensions. It's rather a large generalization from 1D to 2D. When you go from 2 dimensions to higher dimensions, nothing changes. Essentially, 1 dimension is simple. 2D is a little bit more complicated, but higher dimensionality than 2D is the same as 2D. And so I don't think we'll probably get to that, but I've got the slide deck here in case we have time. So I want to introduce the concept of stability, and I apologize in advance that the notation is going to jump around a little bit because the way mathematicians tend to write equations for dynamics looks slightly different from the way biologists tend to do it. And so the Herbert's textbook has all of this material actually in the appendices. It's actually quite a good chapter on stability theory. And I'll try to reference that as much as possible. But the standard mathematical notation is sometimes a little bit different, and there are multiple notations. And so I will apologize in advance if the notation is not always the same. Generically, if we have some set of concentrations, and we're going to write this set of concentrations as a vector, and we're going to do one-dimensional analysis, but this is a general, the concept of stability in fixed points is a general one. So concentration x1, comma x2, comma x3, comma x4, comma xn, we'll use a star to indicate that of particular value is a fixed point. And that means that the derivative of x, the vector, is 0 when we evaluate the rate equations at that particular point. And I've called out this value lambda as a parameter because when we look for bifurcations, what we're looking for is changes of the number or stability of fixed points. And therefore, stability really only applies as a concept when we're thinking about parametric equations. So here we have some point in space x star. We have a dynamical equation d by dt of the vector x is some vector function of x. which depends on the parameter lambda. If d by dt of x is equal to 0, and that's the vector 0, when evaluated at x star, then we say it's a fixed point. Conceptually, x star is a stable fixed point if we start near x star, and we'll explain what near means in a minute, and we come back to x star. And it's an unstable fixed point if the trajectory diverges from x star. And so a classic example of this would be if I have a bowl, and I have a ball, and I put a ball in the ball will roll to the bottom and stay there. That's a stable fixed point. If I turn the bowl upside down and put the ball on top, if I balance it, it won't move, so it's a fixed point. But if I push it a little bit to the side, it'll roll off. So that's an unstable fixed point. And again, there's some differences in notation. If I take the derivative of the function x with respect to time, and I want to evaluate it at a given position, I typically use a vertical bar and then the point at which I'm evaluating it underneath. So you'll see that notation. Okay. So let's think about this now in one dimension. Suppose that I have an ordinary differential equation, d by dt of x is some function f of x. That function depends on a parameter lambda. Of course, it could depend on multiple parameters. And I'll say that x star now is a scalar value of lambda is a fixed point if f of lambda evaluated at x star of lambda 0. And so, for example, here I've drawn a picture. Here is f of x, and 0 is a long line along the middle as a function of x. And you'll see that f of x crosses the line 0 3 times. It crosses it at 0, it crosses it at a half, and it crosses it at about 0.9 something. And so that means that f has 3 fixed points, x1 star, x2 star, x3 star. And so if I know the rate equation, f, and I want to evaluate it graphically, I simply plot f of x and look where it crosses 0. X star of lambda is a stable fixed point if for initial values x naught near x star, x of t goes back to x star. And it's unstable if it moves further away. And I'm going to start out by writing that explicitly. I'm going to use a little bit of math here. X of t is x star of lambda. That doesn't change. Plus some small perturbation epsilon that's going to evolve in time. X star of lambda is stable if there's a delta such that for any epsilon 0 less than delta, the limit as t goes to infinity of epsilon of t is 0. So for all initial perturbations within some range, I come back where I started. In 1D, that's pretty trivial. In multiple dimensions, it gets a little bit more complicated to understand what that means. If I run the time series, and we did this last week, or 2 weeks, or 3 weeks ago, I can see pretty clearly what happens. Here, x1 star is a stable fixed point because for a whole variety of initial conditions, I come back to that fixed point. X3 star is also a stable fixed point. There's a big range of initial conditions which come to that. X2 star, this one in the middle, is an unstable fixed point. If I start exactly on X2 star, I stay there. If I start even a tiny bit away, I move away to one of the other fixed points. Okay, does that make sense so far?
Yes, yes.
I realize that sometimes the math seems to be doing a lot of effort to show something that's obvious, but again, when you do it in multiple dimensions, you do the same analysis, and then it's not so obvious. Okay. All right. So let us actually do this. We're going to start out with a position x naught, which is x star, our fixed point, plus some small perturbation, epsilon of 0. And the time position at all times will be x star plus epsilon of t. And so now we're going to plug x of t in to our equation. So d by dt of x is equal to f of x, which is x star plus epsilon. So I just write that out. And I'm writing it this way because I'm going to do a Taylor expansion of the right-hand side here and eliminate x star. Okay. So the first thing I'm going to do is on the left-hand side, I have the derivative of x star plus the derivative of epsilon. Well, x star is a constant, so that's 0. And so now I have d by dt of epsilon is f of x star plus epsilon. And now I'm going to Taylor expand the right-hand side around x star. And so I have d by dt of epsilon is f lambda of x star of lambda, which, by the way, I know is 0, because that's the definition of x star, plus the derivative of f with respect to x, evaluated at x star times epsilon, plus higher order terms. Excuse me. And in general, we're going to be looking at what's called linear stability. So we're only going to be looking at f. Occasionally, we'll need to look at higher order terms as well. Okay. So remember that f of lambda, by definition of, the definition of x star means f of lambda of x star is 0. So now I can cancel that first term. D by dt of epsilon is equal to d by dx f of lambda, evaluated at x star, times epsilon. And we'll assume that f of lambda of x star is not 0. If it is, then we have to do more work. If epsilon is small and this value is not 0, then the equation is dominated by the first order term, the epsilon term. And so my linearization is very simple. D by dt of my perturbation epsilon is equal to d by dx of f, evaluated at x star, times epsilon. So this is just an exponential. And so I can solve that because d by dx of f evaluated at x star is just a constant. Epsilon of t is equal to my initial value perturbation epsilon 0 times e to the t times d by dx f of x evaluated at x star. This d by dt of f of x evaluated at x star has a fancy name. It's the Floquet multiplier. We don't need to know that. No, we can just think of it as a value, but we get something very simple, which is if d by dx of f of x at x star is less than 0, if it's negative, then this is a decreasing function in time. If the derivative is positive, it's an increasing function in time. If the derivative is 0, then we have to look at higher order derivatives. And so we have something very simple. If the derivative of f at x star is negative, we have a stable fixed point. If the derivative of f at x star is positive, we have an unstable fixed point. So if we plot f, we don't have to do anything. We just look at the slope where it crosses 0, and we know immediately whether the fixed point is stable or unstable. So here, if we have f of x, and it crosses 0, and it's decreasing, we have a stable fixed point. If we have f of x and it's 0, and it crosses 0 increasing, it's an unstable fixed point. If it's tangent to 0, it's a neutrally stable fixed point. So let's look back at our original example. Here, our line crossed 0, and it was decreasing. It was a stable fixed point. Here, f of x crosses 0. It's increasing. It's an unstable fixed point. Here, it's decreasing again, crosses 0. It's a stable fixed point. And so the stability I can see immediately simply from plotting the rate f of x, where the fixed points are and whether they're stable or unstable. All right. Now, what is a bifurcation? Bifurcations happen when we change lambda, not x, but lambda. So if we have a function, dynamical equation dt of x is f of lambda of x, we say that lambda is a critical value at which a bifurcation occurs if the number or stability of the fixed points change for lambda a little bit less than lambda critical versus lambda a little bit bigger than lambda critical. It also means that if f of lambda of x is smooth, differentiable, in both lambda and x, then the slope of f of lambda at x at the critical point has to be 0. That's why we have to consider those tangencies. So let's think about how that could happen. If our functions are all smooth and differentiable, if they're not continuous, all bets are off. Things can be more complicated, and if they have kinks in them, things can be a little bit more complicated too. Then the number of stable fixed points minus the number of unstable fixed points is always constant as we change the value of lambda. And so whatever it is, as we change lambda, it stays the same. So let's suppose that I have, here is f of x as a function of lambda, and I'm going to change the values of lambda. And suppose that as I increase lambda, my line moves down. So maybe my function is minus lambda. So initially, if I look at lambda 1, this doesn't cross the 0 line at all, so there's no fixed point. I increase lambda a little bit more, still no crossing. There's still no fixed point. I increase a little bit more, and I have a tangency. My value is just 0 here. The derivative at that point is 0, and so I have what's called a marginally stable or neutrally stable fixed point, and I don't really know what happens there. If I increase lambda a little bit more, I now know what's going on. I cross the 0 line twice. On the left, I'm crossing it going down, so I get a stable fixed point. On the right, I'm crossing it going up, so I have an unstable fixed point. 1 stable minus 1 unstable is 0. So the total number of fixed points is total number of fixed points is 0. And I keep going, and I still have 1 stable and 1 unstable fixed point as I keep increasing lambda. Another way that things can happen is that I can have a fixed point where I have an equation. This equation looks like a quadratic. If I have something that looks like a cubic equation, I can bend my line. So suppose f lambda 1 of x is a decreasing function of x. So I have a stable fixed point here at the crossing. And now I increase lambda, and I begin to get a sigmoidal shape. At lambda critical, my line is now not crossing, going down. It's tangent at the fixed point. And if I keep crossing, I now get something that looks like a cubic, where I have a decreasing crossing, followed by an increasing crossing, followed by a decreasing crossing. So in this case, I go from one stable fixed point to one stable, one unstable, and one stable again. And so that's two stable minus one unstable is one stable fixed point. Okay. And that's really all there is in one dimension. Okay. So there are a couple of possibilities here. One of them, notice that if I come back here before I move on, notice that I started out with a single stable fixed point in the middle. And at the transition, this fixed point goes from stable to neutrally stable to unstable. So that initial fixed point continued to exist, but switched stability from stable to unstable. If I look here, I had no fixed point. I create a neutrally stable fixed point, and then it splits into a stable and an unstable fixed point. So in this case, if I were to go up, I would see two stable fixed points, a stable and unstable fixed point. They come together, they collide, they annihilate each other, and then I have no fixed point left. In this case, I always have one fixed point, even when I'm done. So I can have two possibilities. I can have a stable fixed point that a stable and unstable fixed point that collide and disappear. That's a change in the number of fixed points. Or I can have the slope at which I cross the zero line change, in which case I can go from a stable to an unstable fixed point by rotating that way, or an unstable to a stable fixed point by rotating the other way. So this is an example we did in class already in homework, where we have autocatalysis. And if you'll remember, we wrote this as a simple gene regulatory network circuit, and we could in principle have that either be without messenger RNA or with messenger RNA. If we remember our rules from the other time, when we see a circuit like this and you say it's gene regulatory circuit, we have to interpret it. Here's our gene, here's the promoter sequence. We have to remember that there's always decay included, even if we don't draw it here. We're not going to use the messenger RNA one today. And then we had to interpret that as a Hill function. And so we say that the rate of production of A is K basal plus V max, A to the H over, and here I'm scaling it by a half. So A will be between 0 and 1. A to the 1/2 to the H plus A to the H. And we don't really care how fast this is moving, so we'll set V max to 1. And then we'll include the decay kinetics, D1 times A. And so this circuit gives us dA by dt is K basal plus A to the H over 0.5 to the H plus A to the H minus D1A. Now, this equation has 3 parameters in it. It has K Basel, it has D1, and it has H. And we're going to analyze the bifurcations as a function of K Basel and D1. And we already did this numerically. We plotted the fixed points as a function of K Basel and D1 back 2 weeks ago. So let's just do this analysis by hand. If K Basel were 0, remember, what is a fixed point? A fixed point is a value of A where the right-hand side of this is 0. If K Basel is 0, we have to do a little bit of work to find out what that fixed point is. If K Basel is 0, one fixed point we get for free, which is A star equals 0. 0 to the H minus D1 times 0 is 0. So 0 is always a fixed point if K Basel is 0. And so let's start out by setting K Basel to 0. Let's make the decay rate 1, make our life easy. And then our function is just f of A is A to the H over 0.5 to the H plus A to the H minus A. And if I plot that, this is what I get. And this is, in fact, the one that I showed at the beginning. The value of H depends a little bit on the value of H. And I think I used H equals 2 for this one. I'm embarrassed to say I don't remember the value of H that I used. It either was 2 or 4. Okay. And again, we can just look at this and we know the stability immediately. This is decreasing, so it's stable. The middle one is increasing, so it's unstable. The third one is decreasing, and so it's stable again. And so this means we have 2 stable fixed points. The first one at 0 and the middle one at 0.5, we know the values exactly. The top one around 0.9 is not so simple to get the value. You have to invert the equation to get it. And that's what we saw. Just checking that it works. Now, let's turn K Basel on. K Basel moves our curve up and down. It doesn't change its shape. And so if we make K Basel bigger than 0, we shift f of A up. And what happens as we do that? Initially, our fixed points were at 0, 1/2, and 0.9. We slide this up a little bit. Our fixed point at 0 moves to the right. Our fixed point at 1/2 moves to the left. Our fixed point at 0.9 moves to the right again. If we make K Basel 0.2, we find out that this fixed point here, the green and the red collide with each other, and we'll get a critical fixed point there. And we make it a little bit bigger than that. What we'll see is the line has the same shape, but it doesn't cross 0 anymore. And so those pair of fixed points have disappeared. So we only have one fixed point, which is the one at the top. And that actually makes some sense. If we have a lot of production which is independent of the value, then we expect the value to be high at all times. So this is an exercise, a little exercise that you might want to do. if you have Colab running, just as a practice, plot the value for this equation. You may already have done this when you did the homework problem. Plot the value of K Basel plus a to the h over 0.5 to the h plus a to the h minus d1a as a function of a, and then replot it for K Basel between 0 and 0.3. You could use steps of 0.05, for example. Okay, and then write the time series for, you have to always try high and low initial conditions to see what's going on. And if you want to do this says we did it in class. If you want to find the unstable fixed points, there's a very simple trick to do this. And I actually gave out code last year, and I have to find the link to do it. But you can do it by hand in about 30 seconds, which is a fixed point which is unstable in forward time is stable in backward time. So if I write the equation dA by dt equals minus K Basel minus a to the h over 0.5 to the h plus a to the h plus d1 times a, and I run that, then my unstable fixed points become stable, and my stable fixed points become unstable. The thing that I have to watch out for is that for some initial conditions that will give rise to divergent solutions. And so I have to try various initial conditions. I have to stay close to the unstable fixed point to find it. Okay, do you want to try that exercise? I think you have a lot of the code you need already from the previous lecture.
Yeah, I can I can write, but I think this conclusion is quite clear because it's just flip the function upside down. So
okay, if you don't think you need to do it, we can skip this one.
yeah, I think we can skip.
That's fine. Again, depending on what your people's background is, it can be useful or not, but I'm happy to skip over. Okay. All right. So when you do this, what you'll find out is, for example, here's K Basel equals 0.1. You'll still see two stable fixed points. When you get to K Basel 0.2, something rather interesting happens, which is there's clearly only one stable fixed point, this one up here. But if I start near where that old fixed point was, I sit there for a long time and then I jump away from it. And that's because here, when I have this value of f that's almost 0, the rate of change is very slow, and I have what's called the ghost of a fixed point. And so it looks here at times 2.5 to about 10, almost as if I have a fixed point there. But if I wait long enough, I move away from it. And that's called the ghost. Okay. And we did this analysis and actually plotted the fixed points as a function of K Basel. We did this a few weeks ago. Here I've actually colored the fixed points to show their stability. The blue one is stable as we increase K Basel. Green one is stable as we increase K Basel. This orange one is the unstable fixed point. And in the code that I've got here, which you have access to in the student materials folder, the way I did it, it plots the vertical line where the fixed points merge. You can change the code, write a little bit of Python to get rid of that line because the line isn't really there. Okay. So the other parameter that we have is the decay rate, d1. And the decay rate, d1, changes the curve in perhaps a slightly more interesting way. Effectively, instead of shifting the thing up and down vertically, it rotates the curve around the zero fixed point. And so here, we're going to take D1 to be 0 to begin with, and then we're going to increase the value of D1. And if we have the value of D1 0, we actually get something that looks like this top curve. We just get the sigmoid from the Hill function. And the only place that crosses 0 is 0. So the only fixed point is a fixed point at 0. And actually at 0, that fixed point is unstable. So that happens. Now I'm going to increase D1, and this line here at large values is going to start coming down. And here I see that line, that my f of a line is crossing 0 at 2 approximately. And when it does that, it also crosses at here about 0.25. And because I know that fixed points have to be generated in pairs, I create a stable fixed point decreasing at 2, an unstable fixed point at 0.25. If I keep increasing D1, the stable fixed point, the large stable fixed point, moves to the left. The small unstable fixed point moves, the middle unstable fixed point moves to the right. The value at 0 doesn't change, it stays there. And at a certain point, this red dot and the green dot are approaching each other, they collide, and that happens for a value of D1 about 1.2. And as I keep increasing things, now my value of f is always under 0. And so my only fixed point is at 0. And so here, my upper branch has disappeared. When I increased K-Basel, my lower branch disappeared. My lower fixed point disappeared, stable fixed point disappeared. As I increase the decay rate, the upper fixed point disappears. The only fixed point is 0. And that makes some sense. If I get rid of things very rapidly, I can't produce enough of it to have anything survive. And again, we could do the same exercise of plotting f of a versus a for different values of D1, get these curves. And I do have code that'll do this for you in the student materials folder if you want to do it. For the time series, we can see the movement of the fixed points. And we'll see again, if D1 is 0, we have a fixed point at 0, and then for all other values, the value a blows up, goes to infinity, which is not what we want. For finite values of D1, we'll have a high value that's stable, intermediate value that's unstable, and 0 stable. If we make D1 too big, then we only get a stable fixed point at 0. No matter where we start, we always wind up with 0. This is what that looks like. So if D1 is 0, our values increase in time. For intermediate values of D1, we have stable and unstable fixed points. If D1 is too big, no matter where we start out with, everything disappears. Okay. And we can do the same bifurcation analysis here. As we increase D1, we had to be a little bit careful, because if we make D1 0, that stable fixed point, the large stable fixed point, goes to infinity, so we can't plot it. But here we see the stable fixed point stays at 0. The stable fixed point, the high stable fixed point, comes down rapidly as we increase D1. The unstable fixed point goes up a little bit until it collides at around 1.2, and again, they disappear. All right. So those are some examples of bifurcations, and we can ask the question, can we categorize the patterns of bifurcations? There are actually not that many things that can happen in one dimension. We can say, can we categorize them? How many are there and what do they look like? And the mathematics for doing this is going to be, again, the standard way of doing it in mathematical biology or dynamical systems textbook is written a little bit differently from what you're used to. And I apologize in advance for using slightly different notation. I'm going to follow the textbook notation for this. So again, if we have a first order differential equation, dx by dt is f of, and here instead of writing f sub lambda, I wrote f of lambda, comma x. At a bifurcation, the number of stability of fixed points change. And there are a series of reduced forms, which are known as canonical forms, which are essentially given by the Taylor expansion of F. And it winds up that there are only 4 possible bifurcations in one dimension, of which we've seen 2. What are called saddle node or tangent bifurcation. The tangent bifurcation is the first one we looked at. Transcritical or exchange of stability bifurcation, and then supercritical or pitchfork bifurcations, which are a little bit more interesting. And let me just go through those so that you've seen them. Okay. Why are these, what are the canonical forms? Well, the canonical forms are ways of basically rescaling things, moving things around to make the mathematics line up. And in particular, in a canonical form, you adjust f of lambda and x so that the bifurcation always happens when lambda is 0. And you can always reassign lambda to be lambda plus minus something to shift it horizontally. The other thing that we do is we adjust the value of x by adding or subtracting a constant to it so that x star, the fixed point, is also at 0. Now, in our previous case, the bifurcations were not at lambda equals 0, and the values of x star were not at 0 either. So we're shifting both in lambda and in x. Okay. So we're now going to write dx by dt as f of lambda comma x. We're going to Taylor expand f around x star equals 0. And so we get f of lambda comma x is a naught plus a1 times x plus a2 times x squared plus a3 times x cubed. Well, let's suppose that a1 is not 0 and everything else is 0. The lowest order form of this is just f of lambda comma x is a naught plus a1 times x. Bunch of lines going down like that. As I change a naught, this shifts to the left, but it doesn't change the slope. And so there's no bifurcation because I'm always crossing the 0 line by going down. So I have one stable fixed point, always. The next possibility would be that a1 was 0, but a2 was not 0. My quadratic term was not 0. And so now I have a quadratic form. So I have a parabola. And now if a naught is negative, I'm below the x-axis. So I have no fixed point. And now I increase a naught and I shift up. I assumed A2 is negative here. I shift up, and I'll get to a point where I cross the x-axis. And so I'll go from having no fixed points to having two fixed points. One where I'm increasing, so unstable. One where I'm decreasing, so I'm stable. I can actually rescale my equations here. So f of lambda comma x is just a naught minus x squared. And if I rescale lambda, then I get lambda minus x squared. This is what I've drawn there. And that's the first canonical form. This is called a tangent bifurcation because this quadratic touches the x-axis in a tangent. So it looks like that. Now, here I've drawn the function. If I plot the positions of my fixed points as a function of lambda, if lambda is negative, I'm under the x-axis, and so I have no fixed point. When lambda is 0, I'm tangent. That's here. And as lambda increases, I get a stable and unstable fixed point, or it's actually unstable and stable fixed point. And so here is my unstable fixed point, here's my stable fixed point, and they move apart from each other as a quadratic, basically reflecting the fact that this is a quadratic equation. And so if lambda is negative, I have no real fixed points. If I have lambda positive, I have fixed points at plus minus the square root of lambda. Stability f prime of this is just minus 2x. Minus 2x for lambda negative is positive. For lambda positive is negative. And so the negative fixed point is unstable. The positive fixed point is stable. And here's a reference to an example I didn't do, but you can do this for a variety of different simple one-dimensional ODEs. There's a classic textbook example called the spruce budworm equation, which has this particular kind of bifurcation. Now, the next order Taylor expansion has A1 not 0 and A2 not 0, and no value of A0. A0 is 0. This has a bifurcation if A2 is negative. And again, we can rescale x to scale out the square root of A2. And so we wind up with f of lambda is A1 divided by square root of A2 times x minus x squared. We can rescale lambda by A1 over square root of A2, and we wind up with a simple canonical form, f of lambda comma x is lambda times x minus x squared. What does that look like for our function? Well, minus x squared, again, gives us that inverse parabola. But now, instead of moving it vertically, we're adding lambda x, which is moving it along the diagonal. And so here I've plotted the results for different values of lambda. Here, you'll notice they always cross the x-axis at 0, but there also is another crossing somewhere else. If lambda is, let's see which way it goes. I'm going to have to look myself. If lambda is big enough, well, we'll see what happens. You could tell me which direction it goes as I change lambda. If lambda is negative, then I'm shifted to the left. If lambda is positive, I'm shifted to the right. The functional form here looks a little bit complicated, but if I actually look at the fixed points, they're quite simple. I want to know when is lambda x times minus x squared 0. Well, I can solve this easily enough. I can factor it. This is x times lambda minus x. So I have a fixed point at x equals 0 always. And I have a fixed point at lambda minus x equals 0. In other words, x equals lambda. So I always have two fixed points, 0 and lambda. What about stability? F prime of x is the derivative of this. That's lambda minus 2x. Lambda minus 2x, well, if I plug in 0, lambda minus 2x just gives me lambda. So the 0 fixed point is stable if lambda is negative, and it's unstable if lambda is positive. What about the other one? Lambda minus 2x, plug in lambda, I get minus lambda. So minus lambda is stable if lambda is positive, and unstable if lambda is negative. And so the fixed points here are very trivial as a function of lambda. They're just straight lines. Lambda equals x equals 0 is always a fixed point. Lambda equals x is always a fixed point. And so I always have two fixed points. But notice the fixed point at 0 goes from being stable if lambda is negative to being unstable if lambda is positive. The fixed point at x equals lambda is unstable if lambda is negative, and stable if lambda is positive. And this is called a transcritical bifurcation. I didn't change the number of fixed points, but I did change the stability. The stable one became unstable. The unstable one became stable. Okay. Is that making sense so far?
Yeah.
Okay, good. All right. What's the next one? The good news is there are only 4, so we don't have to go too far. The next one is that A2 is 0 and A3 is not 0. A0 is 0. So this is the first cubic bifurcation. And so we write f of lambda comma x is a1x plus a3x cubed. Notice immediately I know that x equals 0 is a fixed point. So I can factor that out. It's x times a1 plus a3 times x squared. You rescale by a3 to the 1/3 minus 1/3 to get rid of that a3. And we rescale lambda by a1 times a3 to the minus 1/3 to get rid of the a1. And that reduces this equation to the form lambda times x plus or minus x cubed. Again, these scalings of x and lambda are just to try to make things more comparable to each other. When you have a particular differential equation, you won't have that rescaling. If you want to do that, you have to do it by hand. And so we write here f of lambda comma x, lambda x plus minus x cubed. In this case, we're going to write it out x times lambda plus minus x squared. So this has this kind of a shape as we change lambda. And this one has a little bit more interesting results, depending on whether it's a plus or a minus for the x. Let's assume it's a minus. I have lambda minus x squared times x. I always have the 0. So I have a fixed point at x equals 0, always. Lambda minus x has a fixed point at plus minus square root of lambda. So I have 3 fixed points when lambda is positive. If lambda is negative, the only fixed point that I have is 0. If lambda is positive, I have 0 and plus minus square root of lambda. And this is called a pitchfork bifurcation because it looks like a pitchfork turned on its side. I have a line coming in, and then I have 2 quadratic lines coming out and a central tine in the middle. If I do the stability, I get lambda as I take the derivative, and then I get the derivative of minus x cubed, so minus 3x squared. What's my stability? At 0, I have a value of lambda, and I've assumed that lambda here is positive. Sorry, if I assume lambda is negative, then I have a stable fixed point. If lambda is positive, then that fixed point at 0 is unstable. If x is equal to plus minus square root of lambda, I have minus 3 square root of lambda squared, minus 3 lambda. Lambda minus 3 lambda is minus 2 lambda. So if lambda is negative, it's a positive number. If lambda is positive, it's a negative number. So both of the fixed points, plus minus lambda, square root of lambda, are stable. And so in this case, I go from one stable fixed point at 0 to an unstable fixed point at 0, and in addition, a stable fixed point at plus lambda, root lambda, and a stable fixed point at minus root lambda. This is also known as a supercritical bifurcation. The last one that I get is x times lambda plus x squared. And this one in general is not very exciting, not very interesting. Let's come back for just a second. In this case, I have 2 things going on. I have a single fixed point, the 0 fixed point, which changes stability, goes from stable to unstable. And I have the appearance of 2 additional fixed points. Remember my rule about stable minus unstable. On the left, I have 1 stable fixed point. On the right, I have 2 stable minus 1 unstable is 1. So I have a net 1 stable fixed point for this. If I switch to x times lambda plus x squared, well, if lambda is negative, then I have always my fixed point at 0, plus I have a fixed point at plus minus square root of minus lambda. If lambda is positive, I have my fixed point at 0 and nothing from the other term. If I do the stability analysis, things flip, and so my stable fixed point is in the middle. My 2 quadratic fixed points are unstable, and as lambda gets bigger than 0, I get an unstable fixed point. This in general is not something that is too exciting to look at, but it happens. It's it's exactly the flip of the one we looked at. That's why it's called an inverse pitchfork bifurcation or a subcritical bifurcation. But what would happen here is if you increase the value of lambda, you have a stable fixed point, a stable fixed point. And a lot of times experimentally, you see stable fixed points, but not unstable fixed points. And so what would happen here diagnostically is as you change lambda, as you increase lambda, you have a stable fixed point that disappears because it has these 2 unstable fixed points that collide with it. And so again, if you compare these two, here you have a stable fixed point that splits into 2 stable fixed points and an unstable. Here you have a stable fixed point that collides with 2 unstable and becomes unstable. Again, the rule stable minus unstable, 1 minus 2 minus 1 minus 1. So the next question is that all that you have? And the answer is yes, that's all you've got. In one dimension, for differentiable continuous functions in f, there is nothing else. Those four functional forms are everything that you can have. For one dimension ODEs, first order ODEs, you might say, well, is it possible to have periodic solutions or chaotic solutions for the time series? And the answer is no. And there's a pretty little theorem that proves that there are no periodic solutions for first order ODEs. And that's a simple one, so I'll show you the proof of it. It's given in every math bio textbook, I think, because it's so pretty. So suppose that you have some temporal solution to your ODEs that looks like x of t is equal to x of t plus tau. At some time later, you come back where you started. And now I write dx by dt as f of x. And I multiply y. Well, somebody figured out that was the right thing to do. I multiply both sides of this equation by dx by dt. So then I get dx by dt squared on the left, f of x times dx by dt on the right. Okay. And now I'm going to integrate both sides from time t to time t plus tau. And so on the left, I have the integral from time t to t plus tau of dx by dt quantity squared. Well, the integral of a square is positive definite. So that's definitely greater than or equal to 0 on the left. Let's look at the integral on the right. I have the integral from t to t plus tau of f of x dx by dt. But I'm inside an integral sign, so the dt in the numerator and the dt in the denominator cancel each other. Normally I can't cancel dt's, but inside an integral sign I can. And so now I have the integral from t to t plus tau of f of x dx. But x of t is equal to x of t plus tau. So my integral on the right is now the integral from x of t to x of t of f of x dx. And that is x of t is x of t. So integral from x to x is 0, definitively. So I now have the integral of dx by dt squared is equal to 0, but dx by dt squared is greater than or equal to 0. So the only way that integral can be 0 is if dx by dt is always 0. And so if I have any return of value in a 1D first order ordinary differential equation, that means that the system is constant in time. There's no temporal change at all. And so that means that there are no aperiodic solutions, no periodic solutions, no non-monotonic solutions. Everything is the same. And so one dimension really is trivial. Now let me talk a little bit about higher order dynamics. I already showed this in a slightly different notation. Suppose that I have n species. It's really, typically we'll call them x rather than n. And we have dn1, dn2, dn3. dn1 is some function of n1, n2, n3, f1, f2, f3. It's really more convenient to put that all in vector notation. dn by dt is a vector, is some vector function of n. And if you've got an undergraduate degree in physics, you'll probably have done linear algebra. So then this should be okay. All right. So what we're going to do is we're going to define fixed points in stability just the way we did before. N vector star is a fixed point of our vector equation, dn by dt is vector f of n, if and only if f vector of n star is 0. So that's now a vector of 0, 0, 0, 0, 0, 0. And our stability definition is going to be the same. If we start near our fixed point, we want the value of that perturbation to go to 0. And so we need to say that for all epsilon now vector rather than scalar that are small enough in magnitude, if we start out with n star plus epsilon, the length of it, the norm of it, goes to 0 as we increase t. Okay, and I'm going to now move to null Kleins, and then depending on how much time we have, we may or may not come back to the general theory of second order bifurcations, which also is a general theory for arbitrary order bifurcations. And the reason I want to do that is that the general theory, first, it's something Rita can cover easily because she knows it very well. And secondly, I don't want to do too much math. And this is, after all, a computational course mainly. And so I don't want to spend the whole day doing theorems and derivations. Although the general classification of second order fixed points is quite beautiful. It's a little bit more complicated. There are a couple of additional ones compared to the ones we just looked at, but not that many. So null Kleins are about global behaviors of systems. A fixed point analysis that we just did said, if we have a fixed point and we move a little bit away from it, do we come back or not? Well, if we come back, we have a stable fixed point, we know what we're doing. If we move away, we don't know what happens. The value could go to infinity, could go to 0, it could go to a different stable fixed point. Usually, for biological systems, we don't have divergences, and so we'll go to some other stable fixed point. And null Klein plots, which we already looked at a little bit without talking about why last time, are a graphical way of trying to understand the global behavior of systems. And a null Klein is actually a very simple concept. If we have a rate equation for a variable x1, a rate equation for variable x2, a rate equation for variable x3, the null Klein for x1 is the set of points where the rate equation for x1 is 0. This null Klein for x2 is the set of points where the rate equation for x2 is 0, and so on. A fixed point then is where all the null Kleins intersect with each other. And generally, the null Klein concept works in arbitrary dimensions, but as a matter of practicality and for graphical purposes, we really only use it in 2 dimensions. Null Kleins in higher dimensions exist, but we can't draw them easily, and so we don't use them so much. And so to get the null Kleins, we'll set the rate equation to 0 for each rate equation separately. and solve its roots. And this is a little bit awkward to do using antimony. And so I do have, as I said last week, I have code somewhere that does it, but I couldn't find it, and I still have to find it for you. If you're ambitious, you could figure out how to do it on your own. There is SciPy routine that will find null-clines for you, but you have to write the equations a little bit differently from the way we've been doing it. This is a case where something like Mathematica is actually pretty nice. And so you'll see me in the next few things showing some plots that were not generated with antimony tellurium, but were generated with a function program called XPP-aught that finds null-clines very well. And I really need to go back. If you get good null-cline finding code, then we can go back and redo all these pictures for the next year's class. All right. So why is a null-cline useful? Well, for a null-cline, we set each rate equation to 0 independently. And at a null-cline, we know the direction of movement because the direction has to be perpendicular to the null-cline. As I mentioned, null-clines cross each other at fixed points. So let me give you the procedure for finding null-clines and using them. And again, this is something that we can do graphically. We don't have to do a lot of mathematics for it, although we can. And so we'll assume that we have we're in two dimensions. We have two variables, but it works for arbitrary dimensions, although we can't draw it in higher dimensions. So suppose that we have a set of equations. We have a rate equation for, and again, I apologize that sometimes it's u, sometimes it's x, sometimes it's n, sometimes it's a for their variable name. Depends what textbook that comes out of, which one they like. So here the variable is called u, and I have d by dt of u sub I is a function of f sub I of u1, u2 up to n. And the first thing we're going to do is find the null-clines. So for each f, we want to find the set of u's for which fi is 0. And then we're going to draw those, we're going to sketch those. And that's the thing that we can't do easily at the moment in antimony, is finding and sketching the null-clines. We can see from the trajectory maps what they are, but we can't evaluate those. And if you look at Herbert's code in his textbook, he finds the null-clines by hand and draws them in by hand. He doesn't have a general algorithm for finding them. But we're going to do things by hand, in which case we can do it. Okay, and so we're going to draw the null-clines and we'll label them. In this case, I've drawn a picture where the x-axis is called u, the y-axis is called v. I find the u null-cline. It happens here to be the horizontal green line, dashed line. I find the v null-cline. That happens to be the vertical dashed red line. And in this case, that everything is easy to work with. Occasionally, the null-clines have strange orientations and shapes, and it makes it a little confusing to draw. Okay. And then the next thing I'm going to do is remember that along the u null-cline means du dt is 0. So that means my movement is, I have no movement in the u direction at the u null-cline. So that means my movement is vertical. It could be up or it could be down, but it's vertical. And similarly on the v null-cline, dv dt is 0. So I have no vertical movement, only horizontal movement. And so what I'm going to do is I'm going to just sketch, I say a bidirectional arrow, just a line, in this case, a vertical line across the green dashed line and a horizontal line across the V dashed line to remind myself what direction I cross. And the thing that is always confusing is you have to remember that the arrow at the U null line points perpendicular to the U axis. And it's really easy to flip it. Okay. And now what I'm going to do is I'm going to go to some spot, any spot in the entire system whatsoever, where I can evaluate is U increasing and is V increasing. So all I need to do is get the sign. I don't need to get the value. I just need to get the sign. Very often, for example, the 0, 0 point, it's easy to evaluate. And at that point, I'm going to label the direction of movement. Am I increasing in the U direction? Am I increasing in the V direction? Increasing or decreasing? And then every time I cross the U null line, the direction in the U direction flips. And every time I cross the V null line, the direction of movement in the V direction flips. And so once I've got one point and the null lines, I know the direction of flow everywhere in the system. And so I now have a global analysis of the dynamics of the system. And so that's pretty powerful without doing any mathematics except finding those null lines to begin with and finding the value of the derivatives at one point in the system. So instead of having to evaluate the derivatives everywhere, I have to solve the roots of two equations, and I have to find the slope at one point. And so that's why it's a nice thing to do. Once I've done that, I typically am going to label each quadrant to remind myself what direction I should move in. Is U increasing, is V increasing, and so on. And then I adjust the lengths of the arrows. First, I may put the direction of the arrows correctly, and then I adjust their lengths, because at a fixed point, the lengths are short, the rate of movement is slow in both directions, to make things come out a little bit. Getting the lengths right is a little more work, and so that one sometimes you have to do numerically. Okay, so let's do this together for a very simple case. So we're going to use the Lotka-Volterra equations. The Lotka-Volterra equations are bilinear equations that were written over 100 years ago to model predator-prey dynamics in ecosystems. Actually, there's not much in the world that biologically that actually follows the Lotka-Volterra equations, but they're very easy to analyze. And so if it's okay with you, I'll give this as a little bit of an exercise. The first thing to do is to find the null lines. So you're going to set du by dt equal to 0, and you'll get equations for u and v. And then you'll set dv by dt equals 0, and you'll get equations for u and v. And you want to sketch those. And just draw it on a piece of paper. And remember to label the null line. Remember to write du dt equals 0 next to the one that is for that, and dv dt equals 0 for the other one. And I'll point out that there may be more than one null line. There may be more than one set of points that are part of that null line. The null line isn't necessarily a single line. All right. And then remember that on the U1, if you make U the x-axis, on the U1, draw little vertical lines across the null line. And on the V1, draw little horizontal lines across the null line. Okay. You want to try that? And let me know when you've got that. worked through, or if you need help. Rita, do you remember learning this? Or it's so long ago that you've forgotten learning it?
Yeah, I did it by myself because I didn't have any class on that. Yeah, but I remember learning it from for myself.
Probably.
But that's fun.
It is. It is. It's a very powerful technique.
Yes, yes.
It's amazing how far you can get just by sketching things.
Yeah. That's when mathematicians feel intelligent. James, for next class, I think we'll be traveling. It's me who is going to be in charge, right? So how do I set this environment? How do I make the invitation? How do I enter? Or is it already ready? Or
As soon as you have your IUID, I will make you a co-host.
I have my IUID, finally. Yes.
So let's talk tomorrow, and we'll work through. We'll set up the Zoom so you're a co-host of it,
Okay, thanks.
and
Okay,
then we'll use the same Zoom link that we have today.
okay, thank you.
Jen, how's it going? Is that making sense?
Yeah, I'm considering the case where both U and V are larger than 0. Looks like it's a circle as well.
So let's see what we got here. So this is one where it's a little tricky because suppose we want du by dt to be 0. If u is 0, then this first one is always 0. So u equals 0, 0 comma v is a solution. There's a second one, which is if v is 1, u can be anything. So the stat of points 0 comma, let's see, for the first one, u comma 1 is a null line of u, and 0 comma v is also a null line of u. So there are two lines. There are two separate lines. So the u null line is this horizontal black green dashed line and this vertical green dashed line. And that vertical green dashed line is a little bit strange because I've said before you need to draw vertical lines across it. How do you draw a vertical line across a vertical line? So actually, this particular example already has something that makes things a little bit complicated in it. The same thing for V. If for V, if I have a V null line, if I have V equal to 0, U can be any value. That's this horizontal red line here. Or if U is equal to 1, V can be any value. That's this vertical dashed red line here. And so this is the null lines. Does that make sense to you at this point? Does that work for you?
Yeah.
Now the horizontal and vertical one in the middle are the ones that we typically would worry about. These ones on the axes are a little funny, but they are there, and so we should mark them. Wherever null lines cross, we have a fixed point. So we have a fixed point where the red and the green line cross here, and another fixed point where the red and the green line cross here. So you have two fixed points here and here. And I should say when two null lines of the same type cross, they don't do anything. So the fact that there's a crossing here at 1, 0, comma 1 doesn't do anything. And the crossing here at 1, comma 0 doesn't do anything. Okay, so the next thing we have to do is draw the direction of our arrows. And so on the U null line, we're going vertically. So we draw some vertical lines. And we can't really draw a vertical line on this vertical line. It doesn't make much sense. So we have to live with that. And we have to remember it's very tempting to want to draw these lines perpendicular to the null line. They're not. They're always perpendicular to the axis. Okay. And now we do the same thing. Well, we could do the same thing for V, which I didn't do here. Okay. So now the next step is to pick a point where it's easy to evaluate du by dt and dv by dt so that we know the sign. We want to know, is du dt positive or negative? And is dv dt positive or negative? And so you don't want to pick a point on the null line. You want to pick a point off the null line. In the case of this, because the functional forms are so simple, it's trivial to do it. So why don't you try doing that next step? So pick some point, a half comma a half would be good. And then just add a half, say, is du dt positive or negative, and is dv dt positive or negative?
Yeah, I have already done that.
Okay, and draw a dot and draw an arrow in the direction, the correct direction. So if I'm here in the middle of this box, and du dt is positive, it goes to the right. If dv dt is positive, it would go up towards that center dot. So what direction does it go if I pick that point at 1/2, 1/2?
The du dt is positive and the dv dt is negative. It's
Right.
moving to the
So it's
lower right corner.
That's right. It's going to the right and down. Perfect. So we're going to do that. And I picked some random point here. And actually I did it a little bit more complicated way than that. So let's see. All right. Okay, I'm trying to think. Let me see if I can annotate this. It's easier to do it. Sorry about that. Let me do it the way I've talked you through it, because the way I've got it here is slightly, here we go, slightly different. We wind up with the same thing, but it's slightly different. So we picked a point here in the middle, and we said the direction of movement is like that, right? Can you see, does that show up okay?
Yeah.
Okay. So that tells us that these lines here, these vertical lines, are pointing down. So they have to match what we have here. And I didn't draw the horizontal lines, but the horizontal lines have to point to the right because of this line here. They have to be compatible. Now, when I cross the V null line, the direction in V flips and the direction in U stays the same.
It's the same.
So if I start here, what direction do I move?
To up and right.
Up and right. Okay. So that means when I cross this green one, I'm going up. When I cross the green one, the direction in U flips, the direction in V stays the same. So if I'm here, what direction do I move?
Left.
Sorry?
Up and left.
Up and left. Okay. Now that means I cross this one horizontally to the left. Finally here, when I cross the V null line, I flip in V and stay the same in U. So when I'm here, what direction do I move?
Down and left.
Down and left. All right. So now I've done the whole analysis.
No.
Go in a circle around that central fixed point. Like that. So it's not so, I mean, it's not trivial to do it, but it's not so bad. The thing you have to get used to is it's easy to flip. It's easy to flip the wrong one. You have to remember by flipping the first one or the second one when I cross. If you flip the wrong one, then it doesn't work. Okay? Does that make sense, Jen?
Mhm.
Yeah, but I'm wondering what will the arrows look like outside this area, like when the U and V are less than 0.
So if I wanted to do that, when I cross this line, what happens? V, the direction of V cross changes, and the direction of U doesn't. because this is a V-null-cline. So the direction in V changes, the direction in U doesn't, so I have to be that way. Now what about over here? Here, I'm crossing a U-null-cline, so the direction in U changes, and the direction in V doesn't. And so it has to go like that.
Yeah, this is yeah, but what happens at, for example, the U is 1 and the V is 0 with the exact point?
At U equals 1
Yeah, the cross.
equals 0. Here?
Yeah, yes, here.
So in this case, it's a V-null-cline, so I'm not moving vertically, but I am moving horizontally. And so I'm going to move that way.
Okay.
And
Okay.
so again, when you have these null-clines that are on the axes like that, it's a little harder. What this is doing, what these two null-clines, these green and red null-clines are doing, is saying that if you start with a positive value of U and V, you never go negative. You never cross. And because it's a population model, if you start with a positive population, the population should never go negative. You should never have negative animals.
Mm.
Now, there's nothing mathematically that says I can't start with a negative value of U and V. But if I started that positive quadrant, I should stay in the positive quadrant. So that's a great question. And so it's often interesting to extend these equations outside of their normal range. And that's a good example of how to do that. Okay, let me better hide my annotation here. Wait a second. Where did my annotation go? Sorry about that. I don't want to carry that mess with me for the whole okay. So
And because the point at 0, 0 is unstable, then you have everything going in the U direction to the infinity. So
yeah, you're going down along the V axis and up along the U axis.
yeah.
So let me, I have this analysis where I did it slightly differently. The thing that I would do when I do this is I would also write in the quadrant dv dt less than 0, dv dt greater than 0, and so on as I go through jumping, the way I just jumped across those things. And again, the reason I do that is because it's if I don't label them, it's easy to forget which direction I'm going. Of course, drawing those diagonal arrows is telling me the same thing. Now, something else, which is dv dt increases in magnitude as you move away from the v-null-cline. Du dt increases as you move away from the u-null-cline. So I've sketched that a little bit by trying to make some of the lines bigger than others, but it's a little hard to get that exactly without doing the mathematics. And here I've drawn those diagonals that we were just drawing. Like that. So that's the sketch that we just did by hand together. And again, the quadrants, quadrant 1, U decreases, V decreases, quadrant 2, V decreases, U increases, quadrant 3, U and V both increase, quadrant 4, U decreases, V increases. Okay. And now you have, I think, from last time, the code. Sorry about the squeaking here. My chair is squeaking. I need to oil the chair. You should have code that will allow you to draw this. you have a fancier code to do it, but you have the code that draws the face portrait. It won't draw the null lines, but it'll draw the face portrait. And so why don't you try that? You'll plug in the du equation and the dv equation instead of the fancy stuff that we had last time. But see what you get with that. Can you find the code that you used to draw the face portrait before from last
Yeah,
week?
it's on my desktop.
Okay, great. So why don't I give you just a minute to do that?
Okay.
Because we don't have that much time left, but I'd like to try a couple of examples using that code. And just let me know when you have it, or if you have any problems doing it, we'll go over it. And Rita, we should share that code with you so you have it to play with.
Okay, thank you. So when should we talk tomorrow, James?
Boy, let's see. How about noon tomorrow?
Okay. Okay, good.
I just sent you an invite.
Okay, thank you.
And let me get you share you the folders for things.
Okay.
And Rita, I shared it to your Gmail account because it's a Google Drive. It's a little easier to share it to.
Okay,
I
okay,
can
thank
share it
you.
to your other account too.
No, it's okay. You can, it's just that I was looking into all accounts.
Yeah, I got this.
Okay, do you want to show me what you your screen share and just show what you got?
I sent the picture to the chat.
Oh, great. That works too. Yep, that looks great. So let's come back to here's the slideshow. So this is what you get using this older, very pretty but older package called XPP-aught, showing the flow diagram. If you do the orbits, you get exactly what you got there. And you'll notice that it's not a perfect circle. I mean, when we sketched it, we drew it as a circle, but in fact, it has to fit this confined geometry, and so things get rather angled when you get to small values. It gets almost vertical. But when x is small, when u is small, it's almost vertical in v. When v is small, it's almost horizontal in x. But you see, there's only one fixed point. And that fixed point is at one, well, there are two fixed points actually. There's 0, 0, where there's nothing. And the other fixed point is at 1, 1. The Lotka-Volterra equations are actually a little bit awkward from the point of view of doing dynamical systems, because the 0, 0 fixed point is unstable, but the 1, 1 fixed point is actually neutrally stable. It's not, we don't normally use things which are neutrally stable, but this one happens to be because of the linearity. All right. So again, you find the null lines, you sketch the null lines, which is the hard thing with Antimony. Then you sketch the bidirectional arrows until you know which direction you're going, remembering that along the UI null line, you have to go perpendicular to that axis, not to the null line. And then you pick one point that's easy to evaluate to get the direction of movement. In our case, it was easy to pick a point where we could get both directions of movement. Sometimes it's tricky to do that, and so it's easier to pick one where you know it's along the X and one where you know it's along the Y and do it separately, which is how I'd done it in the slides. Label that point with the arrow, and then just systematically flip the directions and label the quadrants. And then if you want to be a little bit more precise, you could try to adjust the lengths of the arrows a little bit by hand. All right. So here's another one. Why don't we try doing this one? First, this is almost the same, not quite. For example, you can see that u equals 0, comma, v equals anything is a null line. And v equals 0, u equals anything is a v-null line. So why don't you try doing the same thing we just did for this one, and then change your plot to see how it looks, if it looks different. And you'll see the only difference here really is that we've got v squared and u squared instead of u and v. Ah, yeah. So you showed what happens in those other quadrants. That's great.
Yep.
So we have u and v negative. That's great.
Yeah.
This is actually a little bit of a cheat. Because if you're going to find that the null lines are the same. It's the ones you just did.
Yeah. Positive, yeah.
Well, there's the difference that the null lines for the negative values are different, but for the positive U and V, the null lines are the same.
Yeah.
So Jen, is that working for you, or how's it going?
Yeah, it's
All right. So actually the null lines are identical in the positive axis,
Mhm.
and the orbit is almost the same. It's not quite the same. The shape is a little bit different, but it's almost the same. If you look in the negative directions, the null lines are the results are somewhat different. All right. Now let's try another one. This is one that's not so trivial. We still have the U and the V times something, but the arguments are slightly but different. You notice instead of 1 minus V squared, 1 minus U squared, we have U minus V and 1 minus UV. So now the null lines are different. Try this one out, see what you got. This one is beginning to get a little bit more interesting.
Mhm.
Pedro made a comment in the chat that you don't need to do all the Jacobians. Well, effectively, we're doing the Jacobians by hand here. We're approximating them at points where we know the values. But that's a good point.
Hmm.
How's it going for this one? I gave some hints in the chat. How's it coming? Figuring it out okay? How about, does it look, you getting something that looks like this? I know the reason I want people to practice is it does take a little bit of getting used to. So if we look at can people hear me?
Yes, yes.
Okay, great. So if we look at the U, if I set U equal to 0 and V equal to anything, du dt is 0. So I have that u equals 0, v equals anything null line, which is along the x-axis for the u null line. And then if I have u times v equal to 1, I get also a u null line. That's
Yeah.
this line, this red line here. For v, I have v equals 0, u equals anything. That's the x-axis there. And then I also get u equals v, which is this green diagonal line. And so now, remember, dv along the dv null line, I go horizontally. So I've drawn two horizontal lines here. Along the u null line, I go vertically, drawn them there. And here I've already gone in and evaluated the directions. If I start in the bottom here, if v is small and u is large, then what do I get for du dt? If u is small, is large, you set u equal to 1, I get 1 minus 1 times something, that's positive. So in this quadrant here, du dt is positive. What about dv dt? U is bigger than v, so this is positive, and v is positive. So I'm increasing and increasing. So I'm going up and to the right. Now I cross the red line. The red line is the u null line. So the u direction flips and the v direction stays the same. So I'm going up and to the left. I now cross the v null line. I flip the v direction. I'm going down and to the left. I cross this null line. I flip the u direction. I'm down and to the right. And so, as before, I'm circling around this fixed point, but I have rather a different null line structure. And if I then write the code to generate the orbits, what I see is that I actually have a stable fixed point in the middle, that everything spirals into that point in the middle, which is what I think you showed in your simulation. Again, you're doing the quadrants, the negative value quadrants, which are interesting in their own right. In my analysis, I didn't do the negative value quadrants because I was assuming we were talking about positive values. But as you're pointing out, mathematically, there's no reason to ignore the negative quadrants. All right. Maybe we could skip this one for the moment, but this was just an exercise showing that you don't have to know anything about mathematics to do this. Here I drew some random squiggly v null line curve and some random squiggly u null line curve. I gave you a reference point, and then the exercise is essentially to go whenever you cross green, you flip the u direction. Whenever you cross red, you flip the v direction. And you can then annotate that and give the direction for each one of the quadrants. So again, starting with one arrow and the lines, I can draw the dynamics everywhere, even if I don't have equations.
Okay.
All right. And the last one that I wanted to do, and I think this one, we're going to run out of time in a minute, but why don't we bring this up? This is actually a set of equations that are used quite a bit. They're moderately related to the Tank-Hopfield equations that won the Nobel Prize this year, so I guess they're topical. These are called the Fitzhugh-Nagumo equations, which are a simplified model of firing of action potentials in neurons. And the rate equations are a little bit more complicated than the equations that we've written so far. And these equations are chosen partly because they have rather interesting bifurcation behavior. They have quite interesting bifurcation behavior. And you'll see here that they are 1, 2, 3. They're cubic in U, and they're linear on the V side. So the UV one is simple, and the U one is a little bit more complicated. And we're going to have again a bunch of nullclines. U equals 0, V equals anything is a nullcline. So U equals 0, V equals anything. That vertical axis is a nullcline because we don't want the values crossing the axis. We also are going to have, actually, did I say that? I said that wrong because there's a V here.
Yeah.
My mistake.
Yeah.
I better be more careful. I'm getting tired myself. Let's see here. So this one, is this actually, let's see. I mean, I have the nullclines drawn here, but I'm trying to think whether there's an easy way to see what they are. For the second one, for dv/dt, I have C equals U minus V. This is a linear equation. I set this to 0, I get a linear equation. And so the dv/dt nullcline is this one here. And by the way, this one, the values of U and V are allowed to go negative because this is the electrical potential of the neuron. And so I do have negative values as well as positive values. So the V nullcline is a simple linear equation. The U nullcline is a cubic, and I don't have a simple way to see what the, well, actually, it is simple. I just set V equal to U times U minus A times 1 minus U. That's all I have to do. And what are the values? Where is this equal to, where is this part equal to 0? This part's equal to 0 when U equals A and when U equals 1. But this is simply, this line here is V equals U times 1 minus U times U minus A times 1 minus U. So actually the nullclines are easy to construct. So I have these two nullclines. Again, if I'm going to do this analysis, du dt equals 0, that means I'm vertical on the red. dv dt is 0, means I'm horizontal on the green. And why don't you see quickly in my last minute or two, if you use this, if you type these equations in with these parameter values, what do you get for your your phase portrait? And you'll have to adjust your x-axis between about minus 0.5 and 1.5. Your y-axis is compressed, so it goes between minus 0.05 and about 0.2. And if you could, if that works for you quickly, we'll do it tonight. And if not, we'll hold it for next week. You'll notice this one has actually 1, 2, 3, 4 parameters, and there are bifurcations in all 4 of them. But once you have the code to do those phase, the phase portraits, it's pretty easy to change it. This one actually has a rather subtle bifurcation structure. What matters is whether this green line crosses the red line on the left hand of this little minimum or on the right hand. You get different behavior if you move the green line horizontally by a small amount.
Okay.
Yeah, got it. So this is the by hand calculation of the null lines. Again, it's this cycle to the counterclockwise cycle. Here's the flow diagram. And you get these orbits. And I'll leave you with a question, which is, why might this be an appropriate behavior for a neuron? Notice there's only one fixed point. There's one stable fixed point, which is this one where these two things cross. And so ultimately the system sits there and does nothing. But what happens if I push the system a little bit out of equilibrium? I come back, but do I come back right away?
No.
I push it just a little bit here, it stays here. If I push it down, what happens? I flow all the way to the right, all the way up, and then come down along this channel here, back. And so what does the time series for that look like? Time series looks like that. And so this is what's called an excitable system. If I push it in one direction, it comes back and nothing happens. If I push it in the other direction, it jumps way up and then comes back. And that's action potentials have a slightly different functional form. They're a little narrower in the way they fire, but they're not very different. And so this is the simplest set of equations that gives rise to pulses, to excitable pulses. So that's the relationship with neurons. Okay. I think that's it for today. Any questions or comments before we go? Okay, well, I want to thank you for showing up, and I hope this was interesting. It's as I say, this is sort of classic dynamical systems analysis. It would be fun to spend a whole lecture on the Fitsu-Nagumo equations because you could do a lot with them. Here we're using them more as an excuse for motivating the mathematical analysis we're doing. And when we come back to, for example, the equations that Moens has written, we could use these kinds of techniques as well. Pedro, did you have something you wanted to say?
No.
Yeah, I find Fitsu-Nagumo a particularly appealing set of equations. They really do a lot. And so next time we'll do the bifurcation analysis of Fitsu-Nagumo. Because you can get it to do nothing, to not be excitable. You can get it to be excitable, which is what we have here, and you can get it to fire pulses continually as well. And so this is a system where by small perturbations, you can go from being trivial to being pulsatile, to being excitable pulses, to being continual pulses. And it's quite interesting when you look at the orbits because they're not that different from each other. And those null lines really give you a handle on why it's doing what it's doing. Okay, well, thanks everybody. Appreciate you being here.
Okay.
Thank you, Rita, for joining us, and I'll talk to you tomorrow. Okay, bye.
Okay. Bye-bye.
Bye.
See you.
Bye-bye. See you.